Let's talk about conservation of energy and basically the fact that energy is conserved. What does that mean for calculating or for doing physics problems? So the total amount of energy in a process is conserved. This is what we mean when we say conserved. It may change form or be I'm not sure what I was meaning to put here. It may change form, or we'll say be added or removed. And this is talking about in a system. That's strange, but it cannot be created or destroyed. And I'm putting a little asterisk on here because it is a technicality. So you can't create energy out of nothing, and you can't destroy it into nothing. There are ways to kind of eliminate energy, but you're really just putting it into something else where it's not acting like energy. But it's still conserved in a broader scheme. If you have questions about that, or you want to talk about it, let me know, but it's something that we're not going to touch on explicitly in this class, and we're not going to worry too much about. So for a closed system, this looks like the total change in energy, which is going to be the change in energy system 1 plus the change in energy system 2 plus the change in energy system 3, etc., is going to equal 0. No energy goes into or out of the system. For an open system, the total change in energy, change in energy 1, change in energy 2, change in energy 3, etc., is going to equal the energy added as heat or as work, or the energy removed as heat or work. So this is what I'm saying by added or removed. We can add or remove it from our system, but we don't want to create it or destroy it. Now, when we're talking about heat and work, I want to take a minute to talk about these. So you've already talked about work. You already know what that means. So basically, if I do work on a system, I can add energy into it if I'm not considering myself part of that system. Or if that system does work on something else, then that system can lose energy to the surroundings. Heat, you don't need to know much about heat other than it's just a transfer of energy related to differences in temperature. So for example, when I have friction, if I rub my hands together, that friction, that energy is going to kind of radiate away from the place that the friction is occurring, and the rest of my hands will get warm because energy is being transferred away due to that change in that difference in temperature. So where my hands are rubbing, that place is quite warm, everywhere else is cooler, so energy is going to flow through as heat from one part to another. We don't really specify in this class too much which of these. You don't need to worry too much about it. Usually you're just saying energy is leaving or energy is coming in. That's primarily for heat. So if you're saying energy is lost due to friction, you're just going to say it's lost as heat or lost through heat as friction. And again, as we do this, you'll see examples and that'll help clarify things. So here we have a ball falls a total distance of 10 meters. If the ball was released from rest, what is the final speed of the ball? Solve this problem using kinematics and energy considerations and compare your results. So first, we have our traditional kinematics approach. We have a ball that falls a total of 10 meters. So it starts up here, ends down here. Delta y equals negative 10 meters. V initial equals 0 meters per second. V final is equal to some unknown meters per second. And we have A is equal to G is equal to 9.8 meters per second squared. That needs to be negative because it's going downwards. And I believe that's it. Yeah, so delta y, traditionally in kinematics, we're going to use, not that equation, we're going to use v squared is equal to v naught squared plus 2g delta y. So v squared is equal to 2 times negative 9.8 meters per second squared times negative 10 meters. So v is going to equal approximately the square root of 200 meters per second. So we're going to get meters squared per second squared in our square root. I'm pulling them out, so it's going to be approximately square root of 200 meters per second. Let's do the same thing with energy. This is a closed system because we're not thinking about losing energy to air friction. We're not thinking about something pushing or pulling it. So my total change in kinetic energy plus my total change in gravitational potential energy have to equal 0 because it's a closed system. So that means delta Ke, let me use Ke, is equal to negative delta GPE. So now delta Ke is going to be 1/2 m v final squared minus v initial squared, which is going to be equal to negative GPE, which is negative mg delta h. So in this case, you'll notice the m's cancel from both sides, so we don't need to worry about that. And I get that v squared and the v naught squared is 0, so v squared is equal to negative 2g delta h. Now, what's important is this g is not the same as how we're using it up here, because this one gets a negative because we're talking about direction. In this case, we're just using it as a constant to find the weight, right? mg as a weight. So we're going to get 2g delta h. We'll get v is equal to the square root of negative 2 times, in this case, positive 9.8 meters per second squared times negative 10 meters. And you'll see that that ends up also giving you v is equal to square root 200 meters per second. So if that confuses you, flag me down in class and we'll talk more about how this g gets used. But basically, the idea is in this case, we're using it as a constant to calculate the weight, in which case it shouldn't be negative because there's no direction with weight. We're using it as part of the FG. But up here, we're using it as an acceleration, so it needs to get a sign to indicate direction. Down here, we're using it as a scalar. Up here, we're using it as a vector. And this is just an unfortunate aspect of we haven't really used vector notation, but if we were, or if you continue studying in physics, you'll see this in a little bit clearer way. If we consider the falling ball from the previous problem, and in this instance assume that the ball has a mass of 150 grams, and it loses 20 joules of energy as heat because of air resistance, what is the final speed? So in this case, we need to use energy because we haven't learned how to deal with this in kinematics. So I'm going to take what I had written right here, and we're going to just copy that over. So delta Ke plus delta GPE is equal to negative 20 joules. 20 joules is lost as heat. So then we're going to get delta Ke is equal to negative 20 plus delta GPE, and we get 1/2 m v squared, and again remember the initial speed is 0, so we're going to leave that off, and then we're going to get, I'm just going to rearrange these so they're a little bit cleaner, mg delta h, so that should be a minus mg delta h minus 20 joules. And we will get that, in this case you'll see we can't cancel the m's because there's no m on the 20 joules. But we will get that v squared is equal to 2 over m times negative mg delta H minus 20 joules. And then that gives us a V is equal to 2 over m, the whole thing square rooted, times negative mg delta H minus 20 joules. You can run through these calculations, and what you'll find is you do get something less than square root 200. And this makes sense because we've lost some energy due to that air resistance. If you have questions about it, let me know, but otherwise we will wrap up here.